All right, so here we're going to talk about the special cases of solving equations. So far, we've talked about all different types of one variable linear equations. And when I say one variable, I really mean that there's one type of variable in that equation. There's only an x. There's no x's and y's and z's. It's just one letter. And I'm talking about a linear equation because that x and that x, they don't have any exponent on them. That's what a linear equation really means, that there's no exponent. Here we're going to be talking about the special cases of these types of equations. When I say special cases, I really mean that the number of solutions is going to vary. This only really happens when we have variables on both sides of the equal sign. So I'm going to solve these three different types and show you what these different answers might look like, just to compare them. So if I have variables on both sides, really what I want to decide first is which side I'm going to bring my variables to and which side I'm going to bring my constants to. And I'm just going to happen to decide that I'm going to bring my variables to the right side and my constants to the left. It would work just as well if you flip these. It would change the steps, but the same answer would come out. So if I want to get all my variables on that side, that means I have to cancel out my variable terms on this side. So to cancel out this minus 8x or negative 8x, I'm going to add 8x to both sides. That's going to cancel out. That gives me negative 4 equals 6x minus 52. Now I want to bring all my constants to the other side, so that means I have to cancel out this negative 52 or minus 52 on the right side. So I'm going to do that by adding 52 and adding 52. If I do it on that side, I have to also do it on this side. That cancels out. This will give me 48. So 48 equals 6x. So I want to cancel out that multiplication now. Now I'm just canceling out the 6. Here, to cancel out the entire term, I needed to cancel out that x also. So I needed to add or subtract. Here, I'm just canceling out the 6, so I divide that 6 away. And that gives me the answer of 8. X equals 8. These are the types of equations that you've already seen. This is one solution. There is just one answer. X equals a single number. So that's actually not a special case. That's the normal case that you typically see. Now we're going to get into the two different special cases. And actually, I want to look at this equation before I even start. Just looking at these two terms on both sides of the equal sign, I have a negative 2 and I have a negative 2. I have a negative 9x and I have another negative 9x. We have the exact same thing on both sides of the equal sign. I'm still going to solve this the exact same way I solved the equation up top, but you should notice that right away that these are the exact same expression on both sides. They're rearranged, but I can rearrange this to call that negative 9x minus 2 and keep this one the same, negative 9x minus 2. They are exactly the same expression. So I'm going to do the exact same thing. Variables to my right and constants to my left. So I'm going to add 9x to both sides. And you're going to see something weird happening here. This 9x and negative 9x cancel out. And that same exact thing happens on the right side. Negative 9x and positive 9x also cancel out. You don't write anything for that. It's really like 0x if you want to think about it that way. But 0x is just 0. And you would then simplify that into 0 minus 2, which is just a negative 2. So that negative 2 comes down, and this negative 2 comes down. Whoops. No, that's not working, but so we see this answer, and actually it's the exact same thing that we kind of noticed up here. They're the exact same thing on both sides. Negative 2 equals negative 2. If you want to continue with the problem, you can. You can cancel out the constant on this side and cancel it out on that side, and you get 0 equals 0. That is a true statement. You'll see the opposite kind of happens in the other example. I really want to get rid of this highlighting. So when you solve the equation, you get all of the variables and all of the constants to cancel out to 0, and you get that 0 equals 0. You might also notice it way before that, that this expression, sorry, that expression, and that expression are the exact same thing. This expression and this expression are the same, and they're going to continue to be the same on both sides of the equal sign no matter what you do. That tells us that we have infinite solutions. Another way to say that is that all real numbers are our solution set. Oops, all real numbers. We'll talk about that a little bit more in a second. All right, the opposite example is no solution. So actually, let's take a look at the equation beforehand. Looking at the left side and the right side, we have a 16x and we have a 16x, and then we have a negative 11 and a positive 2. You notice that we have the same exact variable term, but different constants. That is the key sign for no solutions. I'm going to keep solving the way I solved the previous two, where I put my variables on the right and my constants on the left. To cancel out the variable term on this side, I would have to subtract 16x. And you're going to notice kind of the same thing that happened in this step happens here. These variable terms cancel out. That negative 16x cancels out the positive 16x. Same exact thing happens here. And you get a weird statement of negative 11 equals 2. Well, you know immediately that can never be true. No matter what we do to this, we can decide we want to cancel out this constant term on this side if we want and get negative 13 equals 0, but that is equally untrue. When you get down to this statement, I would immediately decide that you know you will not be able to solve this equation. Negative 11 will never equal 2. There are no solutions that make this equation true. So I just wanted you to notice the similarities and the difference between these two. You have a variable term on both sides that's exactly the same, negative 9x, negative 9x in that example. Here we have a 16x and a 16x. They're identical variable terms. For infinite solutions, or all real numbers, you also have the exact same constant term. They're the exact same expression on both sides. Whereas for no solution, we have different constant terms. This leaves us with the same constants on both sides. This leaves us with a different one. I'm going to just quickly kind of recap what we talked about here. So just how to identify the number of solutions for an equation and what it looks like. One solution is what you've been dealing with for years now. The last line of the equation will result in x equaling a number. The solution set consists of just one number, such as x equals 10. This is how you write a solution set with braces. They're not brackets, which look like this, and they're not parentheses, which look like that. The braces are indicating that you're stating the solution set, and actually even normally you'll see it as, I might have a little bit of trouble writing those, but x such that x equals 10. That's generally how we write that in math notation, and that might look more complicated than it needs to be, but when you start writing complicated things for that part, this is actually a simpler shorthand notation for it. All right, so that is one solution. X just equals a number. Infinite solutions, or all real numbers. It doesn't actually matter what you plug in. It literally means that no matter what real number you plug into the equation, the left side will always equal the right side. Simple example is 2x equals 2x. It doesn't matter what you plug into that, it will always equal that. You're going to plug in the exact same number there. If you plug in 100, if you plug in 10, it's going to be 200, it's going to be 20, it's going to be the exact same 200 or 20 on that side. No matter what you plug into one side, it always equals the left side. The last line in the equation will result in a true statement. So let's actually keep using that example. If I did 2x equals 2x. If I thought about trying to solve that by combining these variable terms, I would minus 2x from both sides. Oops, that would just equal 0. And I would minus 2x from that side also. That would also equal 0. So something like 0 equals 0 indicates that you have infinite solutions, or that any real number will work. You might also not get down to this step. Let's say I had a plus 10 here and a plus 10 here. You could actually stop at this point where you get 10 equals 10. That is also a good example where the variables cancel out and you get the same constant on both sides and a true statement. The solution set consists of all real numbers. And the way we write that symbol is with a line and then basically attach that line to an R. I'm going to draw that one more time just so you can see how that happened. I draw my two parallel lines there and I just connect this one to that and then start making the R. That is the symbol for all real numbers. All right, and our last example is no solution. Doesn't matter what number you plug in. There is no number that you can plug into the equation and make it true. Let's look at the example 2x plus 1 equals 2x. I can plug in any number I want to that, and that same number going into there. These will never be equal. This expression will always be 1 greater than that expression. I'm going to take that number, add 1 to it. It's just going to be that number that I got originally. There's no way these will ever be equal. The left side will never equal the right side. The last line of the equation will result in a false statement. For example, here, if I were to cancel out the 2x's, I'm going to minus 2x on both sides. That gives me 1 equals 0. That is a false statement. So something like 1 does not equal 0 is the indicator that I have no solutions. And the way I say that as a solution set, it consists of the null set, or you could say the empty set. And I'm going to write that as a 0 with a line through it.